Welcome. This is Steve Fentress on behalf of the Planetarium at the Rochester Museum and Science Center, inviting you to explore exoplanets. The night sky on a clear, dark night. Thousands of stars that we can see with our eyes. Millions more that we can see with telescopes. Astronomers worked for centuries to figure out that those stars we see at night are other suns, trillions of miles away. So far away they look like points of light. But it's really been mostly in the 21st century that we have found definite physical evidence that probably most of those stars have planets of their own. In our initial searches, we have found planets of types we do not even have in our solar system, planets larger than Earth but smaller than Neptune, extremely hot giant planets, planets going around double stars. So far, we have not found Earth 2.0, a planet that is the same size, the same temperature, the same composition as Earth going around a star similar to our Sun. But we've just started looking. To appreciate exoplanet systems, let's spend a moment looking at our own solar system. We're using a program called NASA's EYES, which you can download from eyes.nasa.gov. And it has options you can turn on and off. Very similar in many ways to our Digistar software at the planetarium. Let's put time into fast forward, 1 week going by every second. And we see planets revolving around our sun. Our star, one of about 500 billion stars, we think, in our galaxy, which we call the Milky Way. Our sun puts out light and heat. If we are closer to the sun, we get a lot more light and heat. If we are farther away, a lot less. And the sun's gravity governs the motions of planets in our solar system. Here's a key thing to notice: how long each planet takes to make one orbit around the sun. Mercury goes around once in about 88 days, Earth about 365 days, Mars almost 2 Earth years, and looking back, Jupiter almost 12 Earth years. So planets closer in have shorter years, planets farther out have longer years. Back in the 1600s, the astronomer Johannes Kepler discovered an exact mathematical formula that connects the period of revolution, or the length of the year, to the distance from the planet to the sun. If you know one, you know the other. That's why the first great planet-hunting space telescope was named Kepler. Finding exoplanets is really hard because they hide in the glare of their star. Remember, this is an artist's concept. What we see from Earth is a point of light. European Southern Observatory has a nice piece of artwork showing a transit, a planet that happens to be crossing in front of the face of its star. This would be a Jupiter-sized planet, blocking about 1% of its star's light. An Earth-sized planet would cut off about 1/100% of a star's light. But if you can make a light meter sensitive and precise enough, you can measure the dimming and make what they call a light curve, and the exact shape of that curve is loaded with information about the size of the planet, its distance from its star, and even some information about the star itself. Here's a cartoon of the Kepler Space Telescope in space. Only a fraction of all solar systems could even have been found by Kepler. You want a lucky lineup like this, where, from Kepler's point of view, the planet happens to go in front of the star. A face-on solar system like this, Kepler would never find. Not this one either. Only about 1% of solar systems are aligned well enough for Kepler to find them. That's why Kepler watched 156,000 stars. 1% of that is still a lot of solar systems. One thing that has to be done is eliminating false positives. Suppose you have a star and you think it might have a planet going around it based on its light curve. You have to make sure you're not being fooled by something like this, an eclipsing binary star that's lurking in the background. Or, as you see in this ESA cartoon, a naturally pulsating star. So confirming an exoplanet means eliminating the false positive possibilities. Here's an example of some real data. This is from the Spitzer Space Telescope, looking at the TRAPPIST-1 system of 7 planets. Here's the light curve. And you can figure this out. You'll notice the C's are evenly spaced, the B's are evenly spaced. Each one of those is a transit, and they're color-coded with the planets in the cartoon. Oh, there went a solar flare. That would be bad for life on any of those planets. Real transit data from the TRAPPIST-1 exoplanet system. There are other ways of trying to find exoplanets. This is the radial velocity method. If you take the light from the star and break it up into its rainbow colors, there are dark lines in the so-called spectrum. And if those lines are shifted toward the blue, that means the star is coming toward you. Shifted toward the red, that means they're going away. So by mapping this, it's possible to plot out the orbit of the star, which tells you about the orbit of any planet or planets it has. This can detect planets that are too far out for Kepler to find because they don't make enough orbits for you to see multiple transits. And here's a really esoteric way of finding it: gravitational lensing. When a star and a planet passes in front of a more distant star, according to Einstein's theory of gravity, the light of the distant star is focused for a short time, making a surge in brightness. The disadvantage of this method is that this is a chance alignment that'll never repeat. You'll never see this planet again. Now here's what we all dream of: being able to block out the light of the host star so that you can see the planet hiding in the glare. Really hard to do, and it has only worked for a few systems. Here's one. It's called HR 8799, and this is a movie made from pictures taken over a period of 7 years. So we've got planets here whose orbital periods range from decades to centuries. Direct imaging is what this technique is called. If you want to explore exoplanets on your own, if you can watch this video, you can go to exoplanets.nasa.gov, and there's a lot of cool stuff to explore there. Scenes on other planets, a selection of the weirdest and most remarkable ones. Over 4,000 exoplanets now known to exist. They've been verified by more than one method, and over 3,000 other solar systems. Now this is an interesting graph. It shows the different kinds of planets that have been detected, and notice a very common type is the super-Earth, a type larger than Earth but smaller than Neptune. We do not have any of those in our solar system. Notice most exoplanets so far have been found by observing transits, some by radial velocity, and only a small amount by microlensing or direct imaging. From here you can go to this cool app called Eyes on Exoplanets, which is again a sort of a Digistar-like thing you can play with. And here's our Milky Way galaxy, and the yellow dots are places we have searched and found exoplanets so far. There's the sun in the center, and that thing that looks like a flashlight beam, that's where the Kepler Space Telescope concentrated during its 3-year primary mission. Let's look at a couple of examples. Let's look at a very early Kepler discovery, the Kepler 4 system. Artist's view of the planet, but let's look at the planetary system. It shows you the star, the planet's orbit, and this green ring is the habitable zone, the Goldilocks zone, where a planet would be not too hot, not too cold, to have liquid water on its surface. Well, let's find out about this planet Kepler 4b. Its period of revolution, its year, is only 3.2 days long. So according to Kepler's law, that means it's close into its star. And if we superimpose the orbits of planets in our solar system, what do you think you'll get? Yes, way inside the orbit of Mercury. Short year means very close to its star, as Kepler realized back in the 1600s. Let's look for another cool example here. The Kepler 16 system, and when the PR came out about this, it was called the Tatooine planet because something we didn't think was possible, a planet orbiting a binary star. We have Kepler 16a and 16b, capital A and capital B, and then Kepler 16 little b is the planet orbiting just at the outer edge of the habitable zone in this binary star system. Remarkable, and something we didn't think would exist before. Let's look at that HR 8799 system, the one that was discovered by direct imaging. And we look at the whole system. So this was found by direct imaging, which means the planets are far out. So when we superimpose our solar system on this, what do you think we'll get? Yes, most of the system is farther out than Jupiter is in our solar system. That would make sense. That's the kind of system we can find with direct imaging. Another website to look at is Naming Exoworlds. This is from the International Astronomical Union, and they've done a couple of contests, international contests, to assign dignified, time-honored names to exoplanet systems. Check this out. Each country had a process for selecting a name for an exoplanet system, the star and one planet. And you can look up by country and see the names that they have selected based on that country's history, literature, art. And I will leave it to you to go to the Name Exoworlds website and find out what names were selected in this particular round of naming to represent the United States. Don't forget moons. They can be quite different from their planets. In our solar system, Jupiter's moon Europa has more water than Earth. The Hubble Space Telescope has been used to look for exomoons.
Have scientists found our first exomoon? Looks like they still need more observations to be 100% sure. The moons in our solar system are very diverse, some with liquid water, some that are potentially habitable, so being able to observe moons in different solar systems would give us a whole new treasure trove of interesting worlds to study. The team of astronomers from Columbia University sifted through data from 284 Kepler measurements of transiting exoplanets. A transit happens when a planet passes directly between us and its star and blocks out a small portion of the star's light, which produces a dip in the amount of light coming from that star over time, called a light curve. Out of the 284 planets the team looked at, they found one planet with an extra wobble in its light curve that might be a moon. The team only had Kepler data from 3 transits of this exoplanet, so they sent a proposal to the Hubble Space Telescope to capture more data of this possible exomoon. Hubble can measure light curves much more precisely than Kepler, so Hubble can more definitively confirm or disprove the existence of this exomoon once it gets multiple transits. So far, the team of astronomers has collected Hubble observations of one transit of exoplanet Kepler 1625b. The planet transited across the face of its star for 19 hours, as expected. Then, about 3.5 hours later, a second, smaller dip in the light curve started. That right there is intriguing evidence of an exomoon. The Hubble observation unfortunately concluded before the possible moon finished its transit, so Hubble hasn't yet observed a full transit. This light curve appears like it shows an exomoon, but we can't say it's a definitive detection until Hubble observes at least one more transit. If this is actually a moon, what do we know about it? The planet Kepler 1625b is likely several times the mass of Jupiter. Its possible moon appears to be about the mass and radius of Neptune. Neptune-sized moons are obviously not something that exists in our own solar system, and we're not sure exactly how such a moon would form. Finding planets and moons so different from the ones in our own solar system gives us a lot more knowledge of the many diverse ways planetary systems can exist. In the near future, scientists hope to use the Hubble Space Telescope to try to confirm the discovery of this exomoon. And then they'll use Hubble for follow-up observations of other planetary systems discovered by observatories like Kepler and the recently launched transiting exoplanet survey satellite, Tess. So, if you like planets, and honestly, who doesn't? Stay tuned to learn about all sorts of fascinating new worlds.
The planet-hunting space telescope operating today is Tess, and here's a report on what it's been doing.
Tess, the transiting exoplanet survey satellite, has completed its survey of the southern sky. To do this, Tess divided the southern sky into 13 sectors, and its 4 cameras monitored each sector for nearly a month. Tess was watching for the slight dips in starlight as distant planets passed in front of their host stars, but it also caught other transient events like comets and supernovae, in addition to building a beautiful panoramic picture of the sky. The bright band on the left is the Milky Way, our home galaxy viewed edge-on. Zooming into the mosaic, it's clear how much detail and how many stars Tess has captured. At the center is the continuous viewing zone, where the view of one Tess camera overlaps all 13 sectors. Within it is the Large Magellanic Cloud, one of the closest galaxies to our own. A little farther out is the more distant Small Magellanic Cloud, flanked by a ball of stars, the bright globular cluster NGC 104. Silhouetted by the band of the Milky Way is the Coalsack Nebula, an obscuring cloud of dust in the constellation Crux, also known as the Southern Cross. The mosaic also contains many notable stars, such as Alpha Centauri, one of our closest neighboring systems and among the brightest stars in the sky. Fomalhaut, which hosts one of the first directly imaged planets. Sirius, the brightest star in the night sky. And Betelgeuse, a red supergiant star that marks one shoulder of the constellation Orion. The Orion Nebula, a vast nursery where stars are born, was imaged in great detail by the Hubble Space Telescope. This isn't a cosmic object at all. It's actually a reflection of Rigel, the bright star marking one of Orion's feet, and it's caused by light scattering off part of the camera system. Tess's confirmed exoplanet discoveries are currently distributed all around the southern sky. Many of these discoveries are actually multi-planet systems, and several are Earth-size. Many more candidate exoplanets await confirmation. It's easy to see which sectors were among the first, because astronomers have had more time to study them and find potential transits. Eventually, candidate and confirmed planets will be distributed more evenly around the sky. Tess has now turned around and is observing the northern sky using the same strategy. As it does, astronomers will continue to sift through roughly 20 terabytes of data from the southern hemisphere, as well as the new incoming information. Eventually, hundreds or even thousands of distant worlds will owe their discovery to Tess.
If you like to watch YouTube lectures, I recommend looking for Dr. Natalie Battaglia, who worked on the Kepler project for many years and is now a professor at UC Santa Cruz. Dr. Eric Mamajek was a professor at U of R for many years before he moved to JPL, where he's in charge of exoplanet exploration there. Professor Sarah Seeger has a nice talk on looking for atmospheres of exoplanets. And there, with those lectures, you'll find out about ideas for future research like the star shade concept. The idea here is that you would create a giant shade that would fly tens of thousands of miles in front of a space telescope and be maneuvered into just the right place to hide a star but allow its planets to be seen. Now let's look at our night sky. Some things in our sky in the week starting about April 1st. We have our planetarium program Stellarium running in perspective mode. We face west-southwest and watch the sun set. We stop about 9:15, and there's a lot to look at in that southwestern and western sky just after sunset this week. Brightest, Venus. If you can see anything up there at all, you can't miss it. Unbelievably bright. And look above Venus for a little bunch of faint stars close together, known around the world by its ancient Greek name, the Pleiades, Pleiades, known to kids as the Seven Sisters, even though most people see 6 stars there. And over the next few evenings, Venus is going to pass right in front of the Pleiades. Here's April 1st, April 2nd, April 3rd. The Venus is squarely in front of the Pleiades. April 4th, 5th, 6th, 7th. Let's go back to April 1st. And there's more. Over to the left of Venus, bright orange star Aldebaran in a little group shaped like a letter V, the constellation Taurus the Bull. The orange color of Aldebaran indicates a star cooler than our Sun. Another orange star, Betelgeuse, high in the southwest, easy to see. And then the brightest star in the entire night sky, way over in the south, Sirius. And a good way to confirm that you have Sirius is to look for the 3 stars of Orion's belt. They point to Sirius. Stick figures and artwork of the constellations, at least according to one artist's interpretation. Let's now check the northern sky, about 9 o'clock. We are facing north now, looking higher. Let's look at a wider viewpoint and look for something that may be familiar if you're a star fan. 3 stars in a curve making a handle, 4 stars making a cup. It's the Big Dipper, part of the ancient constellation Ursa Major. The last 2 stars in the cup of the Dipper point to a medium bright star that's always in the northern sky, always in the same place. Polaris, our North Star. As Earth rotates, all the stars make circles every 24 hours, but Polaris stays in the same place. We see satellites going by here. We'll stop at about midnight. There in the northeast, summertime's brightest star, Vega, rising. Let's look east, about midnight. Now something else you can find with the Big Dipper. There's the cup. See the curved handle. Take the curved handle and follow the arc, and you come to a bright orange star, Arcturus. Follow the arc to Arcturus. And after you follow the arc to Arcturus, sail on to Spica, a bluish-white star. Blue-white indicates hotter than our Sun. Orange, like Arcturus, indicates cooler than our Sun. Let's stay up till later. About 3 o'clock in the morning, looking east, three bright stars, Deneb, Vega, Altair, make a giant triangle called the Summer Triangle by skywatchers because summer is the first season most people notice it in the evening. And between Deneb and Vega, look how many exoplanets we found, because that's where the Kepler telescope pointed during its 3-year primary mission. There are thousands of exoplanets and exoplanet candidates in that one little patch of sky. It was a place to start. Let's adjust our viewpoint and go to later in the morning. Morning is coming. Stopping about 5 o'clock. In the south, bright orange-colored star called Antares. Cross over the Milky Way, and 3 planets rising in the southeast early in the morning. And over the next few mornings, those planets will shift their positions. Let's look closer at that arrangement. Here's the morning of April 2nd, 3rd, 4th. See how Mars is shifting its position rapidly. The 5th, 6th. Something beautiful to watch for just before the sun rises over the next week. Let's watch sunrise in early April 2020. Well, thanks for watching Exploring Exoplanets. Next week, a preview of the total solar eclipse coming up in 4 years on April 8th, 2024. See you then.